Vectors, Part 2. Alright, let's talk some more about combining vectors. Let's do an example. Here we have a traditional Cartesian x-y axis, and what I want to go ahead and draw on here are two velocity vectors. So I want to go ahead and draw their magnitude and their direction. The first velocity vector has a magnitude of 10 meters per second, and it has a direction of 30 degrees above the horizontal. So let me go ahead and draw that for you now. So here is your vector representation of v1. Now there's going to be a v2 value as well. The second vector is a velocity of 12 meters per second. And the direction here is 35 degrees below the horizontal. So let me go ahead and draw this one. And so here is your second vector representing v sub 2, or the second velocity. Now, what I'd like you to do is to add these two vectors together, or combine these two vectors together. And so what we're going to do here with these two vectors is we're going to resolve these two vectors into components, and then we're going to add up all the horizontal components, and then separately add up all the vertical components, and then we're going to use Pythagorean's theorem to find the resultant velocity. So let's go ahead and start resolving our vectors into components. So for v sub 1, resolving into components, I'm going to have a horizontal component, and I'm also going to have a vertical component. The vertical component, I want to call that v sub 1y, and the red component, I want to call that one v sub 1x. Now, for my second velocity vector, I want to have a vertical component that I'm going to call, well, let me draw here with green. In this case, this one's going down. We're going to call that v sub 2y. And my other vector here will be v sub 2x. And that's all. These all have the subscripts of y's or x's depending on their direction. Notice that both of these triangles are right triangles. And also notice this angle here, theta 2. It's also theta 2 right here. We're going to need that for when we use our trig identities. So now that we've resolved the two velocity vectors into their components, now what I would like to do is add up all the components in the x direction, get a value for that, and then add up all the components in the y direction and get a value for that. The velocity values, I want to sum up the velocity values in the x direction. In this case, it looks like I'm going to have a v1x plus a v2x. Notice my notation here, I have right here what I'm underlining is the capital Greek letter sigma, and that just means total or sum, and this is of the velocities in the x direction. Now this is where we have to look at the trigonometry ratios to plug in our value for v1x. So using trigonometry, we can also see that v1x is the same thing as v sub 1 cosine of theta sub 1. And v sub 2x is the same thing as v sub 2 cosine of theta sub 2. Let's go ahead and plug in our numbers here. And so for v sub 1, that's 10 meters per second, cosine of 30 degrees, plus our v sub 2 value, which is 12, cosine of 35 degrees. And plugging in the numbers into the calculator, I get our value of 18.49 meters per second. Notice that I added the two components, the horizontal components, and I added them because they're both pointing to the right, and right is positive. When we look at the vertical components, if I just go back to my diagram for a moment, if I look at the vertical components, v sub 1y is actually pointing upward, and v sub 2y is pointing downward. So when we find the total vy values, we will actually be subtracting these because they're in opposite direction. So let's go ahead and do that now. We're going to sum up the velocities in the y direction. That's going to be the same thing as v sub 1y. One way you can look at it is adding it to a negative v sub 2y because v sub 2y is acting down. That's the same thing as v1 sine of theta 1 minus v sub 2 sine of theta 2. So plugging in my values here for v sub 1, I will put in 10 sine of 30 degrees minus 12 sine of 35 degrees. And plugging that into my calculator, I get a value of negative 1.88 meters per second. Now, if I'm going to use the Pythagorean Theorem, I can then plug in values into the Pythagorean Theorem, these horizontal and vertical values that I just found. And I can do this with the following equation. This equation here says my total resultant velocity is equal to the absolute value of the square root of the quantity of my horizontal velocity squared plus my vertical velocity squared. And this is just another way of looking at the Pythagorean Theorem. So let's go ahead and plug in our numbers and see what sort of answer we get. So here we have, I plugged in the numbers into our equation. Notice that my v sub y is a negative 1.88, but when I square that, it ends up being positive anyway. Let's go ahead though and plug it in the calculator. Let's see what we get. And I get an answer rounded to 3 significant figures of 18.6 meters per second. Well, that's wonderful. That's the magnitude. The problem is we don't have the direction. So we still need the direction because we're dealing with the vector. So now we're going to do that. So going back to my original picture, these are my two velocity vectors, their magnitude and direction. What I want to do here is go ahead and redraw this picture so you can really see what the direction will be. In this picture, all we can really tell is that the sum of these two vectors will give us a direction of somewhere in between the first and the second. But really, where is that going to be? So I'm going to sketch this for you graphically. So my first vector comes out something like this, and we call that v sub 1 at a theta sub 1. Now my second vector, when I'm going to draw this to find out the direction, or if I was drawing this to scale on graph paper, what I would do is I would take the tail of my second vector and put it on the head of the first. And I would redraw with the dotted line here my new horizontal axis, if you will, 0 degrees. And I will plot the direction based on that. Now, my second vector had an angle of 35 degrees below the horizontal. So when I draw my vector, the tail touches the head of the first, and it will go down below about 35 degrees, and that's represented here as theta 2. Now my resultant vector will be from the tail of my first vector, and I will connect that to the head of the second vector like so, and this becomes my resultant velocity or my total velocity here. So you can see there is some angle here below the horizontal, which I'll try and represent right here. And the question is, what is that angle? What is that? So we're going to use trigonometry again, the trig ratios. This time we're going to use tangent. And we know that that angle, which I'm calling just simply theta, and that goes right in here, this angle theta is going to be equal to the inverse tangent of the sum of my velocities in the y direction over the sum of my velocities in the x direction, and we had those values on the previous page. So let's go ahead and plug in those numbers now. So these are our values for the sum of the vertical components and the horizontal components. And plugging this into my calculator, I get a direction of negative 5.81 degrees. And that looks pretty close to what the picture is showing here in red. Thanks for watching.